Welcome everyone to our first in a series of videos on electron configuration. Starting in 3, 2. Welcome everyone to our first in a series of videos on electron configuration. Electron configuration is describing where all the electrons are within an atom. So the main energy levels, the sublevels, the orbitals, and so on. Our starting point is going to be the quantum numbers that we've talked about already, and we're going to move to a more visual representation of the electronic structure, which will help us to understand a lot of properties of elements as well as chemical bonding. So in this video, we are going to look at the reason for the order in which the subshells are filled. And then we are going to relate that order to the structure of the periodic table to make a connection there. Recall when we learned about the Bohr model of the atom, one of the properties of the Bohr model was something that was referred to as the Offbow Principle, that energy levels fill from the lowest value of n to the highest. So n equals 1 fills first, and then n equals 2, then n equals 3. Or the first energy level fills, then the second, and then the third, and so on and so forth. So in general, that's true, but it turns out that as we get up to n equals 3, then n equals 4, this doesn't exactly always work. And that's where we have to bring in some sublevels. So recall that at every main energy level, there are a certain number of sublevels in which we find the different orbitals. Sublevels follow a rule in which they order, and they always follow the rule from the lowest value of L to the highest. So within an energy level, sublevels will always fill in the order L equals 0, L equals 1, L equals 2, L equals 3, and so on. Now, from here on out, we are not really going to be using too many of the quantum number designations. We're going to be using the letter designations more. So S, P, D, and then F, okay? That's always going to be the order in which sublevels fill within a main energy level. Now, our challenge here is to put all those together and come up with a rule or a system for understanding the order in which all these different sublevels fill within the atom. So this rule is technically called the Madelung Rule, which is basically an expansion on the Offbow Principle. Orbitals are filled in order of increasing n plus L. So you sum the primary quantum number and the secondary quantum number, and that gives an indication of the relative energy of that orbital. If we calculate the value of n plus L for two orbitals and it's the same, then those orbitals are going to be filled in increasing values of n. So if one value has an n equals 2, the other one has an n equals 3, n equals 2 will fill first, then n equals 3. So once again, this calculation, n plus L, is not some sort of measurement, a quantitative measurement. It gives us an understanding of the relative energy of the orbitals. So let's look at an example here. So let's take a 2p and a 3s sublevel. Okay. Now on the previous page, we did talk about, it did use the term orbital. And so when I'm using the term sublevel, I'm going to use them a bit interchangeably here because what I'm just talking about are orbitals found at the 2p sublevel or the 3s sublevel. Okay. So if we have a 2p sublevel, 3s sublevel, which one's going to fill first? Well, for 2p, n is equal to 2 and L is equal to 1. Remember that for the p sublevel, that corresponds with an L value of 1. So n plus L is equal to 3. for a 3s sublevel, so that is a s sublevel at the third energy level. N equals 3, L equals 0. Remember, an S sublevel is given the 0 designation. N plus L, 3 plus 0, 3. In this case, since N and L are the same, we're going to fill them in order of increasing N. So the 2p will fill first because it's the second energy level, and then we'll go to the third energy level. So 2p fills before 3s. Let's go through another example here. Which sublevel will fill first, the 3d sublevel or 4s sublevel? So 3d, third energy level. D is the letter designation for L equals 2. So 3 plus 2, we have 5. 4s, N equals 4. S is the letter designation when L is equal to 0. So here, N plus L, 4 plus 0 equals 4. So here we have a case where the rule states that sublevels fill in order of increasing N plus L. So 4s fills before 3d. So this is one of the prime examples where Bohr's model for the order in which energy levels fill breaks down. Electrons will first fill the s sublevel at the fourth energy level before filling the d sublevel at the third energy level. Now, we don't need to go through every single example here, but there's a few different ways in which we can help remember the order in which all these sublevels fill. And one is using the Offbow diagram. I'm going to flip over to the whiteboard in a minute here. I'm just going to describe the diagram here. You can see that we have all of the different sublevels for all known elements here, okay? From bottom to top, they're listed from lowest energy level to the highest energy level. From left to right, we go from S, P, D, then F. Okay, so we see the two axes here are the main energy levels, and then the sublevels going from the left to right, S, P, D, F. So let's build the Offbow diagram together. Our first step is to create a vertical axis where energy is increasing from bottom to top. Okay? So as we're building this, imagine that the nucleus is down here at the bottom. And as we move up, the sublevels are getting further from the nucleus. And since they're getting further from the nucleus, they're increasing in energy. Our first step is to write out all of the S sublevels. If you recall, the S sublevel is present at every main energy level. So in the first most leftmost vertical column, I'm going to write out all of the S sublevels, 1s, 2s, then 3s, and so on here. Now this can continue indefinitely, but just for sake of space, we'll just stop at the sixth main energy level. Going from left to right, we are going to write out the sublevels in order that they fill. So remember, they always fill S, then P, then D, then F. So my second vertical column will be the second subshell type that fills, and that's going to be the P-type sublevel. Recall that at the first main energy level, there is no P-type sublevel, so it begins at the second main energy level. Now that I've got two columns, you can see the organization. Going from left to right, we have the different sublevel types. Moving from bottom to top, we have the different main energy levels, or n values. So we align the n values, 3, 4, 5, 6, in rows, going from 1 at the bottom to 6 at the top. Let's continue with the D-type sublevels and the F-type sublevels. One thing that comes up when students view this diagram first is, well, why do we just stop at new sublevels here at F and we don't kind of continue this diagonal going further? Because in theory, according to the quantum numbers, at the 5th main energy level at n equals 5, there should be 5 different sublevel types. Well, let's look at the difference between theory and practice. In theory, that is correct. In practice, you'll see that we only need the 4f and the 5f sublevels to accommodate all of the electrons in the known atomic elements. Now that we've completed the diagram, we're going to add in arrows which go in the order that they fill. This is where the value of writing this out yourself, because we can write out these diagonal arrows in the order that the sublevels are going to fill, and you don't just see the completed diagram. We're going to start at the bottom and write diagonal arrows moving from bottom right to top left. So the first sublevel that fills is 1s. You'll start writing this up here. Once we get to the end, or the S sublevel, we move to the right. The next sublevel is 2s. When I've hit the leftmost column, I move over. 2p, 3s. So after 2s comes 2p and then 3s. After 3s, we've hit the leftmost column. We start another diagonal line. 3p, then 4s. And then after that, we start another diagonal line. 3d, 4p, 5s. I'm just going to do one more here so we can see the pattern. Next step after that, 4d. So moving from bottom to top, we write these diagonal lines, and that shows us the order that the electrons will fill the different orbitals. Note a pattern here that the S sublevel at the next higher energy level will always fill before the D sublevel at the previous energy level. So 4s fills before 3d. And we see that again repeated up here. 5s fills before 4d. As we practice with electron configurations, we'll see how that accounts for the difference between Bohr's model and the quantum model in terms of electron shell capacity and the order that they fill. Our final task for today is to relate the structure of the periodic table to the order that orbitals fill. On my left here, I have a periodic table that's color-coded. Before we get into those color codings, let's remember that in Bohr's model, we saw a relationship between the period that an element is in and the number of energy levels. Simply put, the period number tells you the number of energy levels present for that atom. Elements in the 3rd period have 3 energy levels with electrons in them. Elements in the 4th period have 4. Elements in the 5th period have 5. That doesn't tell you the order and how many electrons are in each, but it just tells you how many energy levels are present. The color coding blocks here relate to the different sublevels. Groups 1 and 2 are referred to as the S block. Recall that an S sublevel has a single orbital which holds 2 electrons. And you can see that the S block is 2 elements across. Groups 13 to 18 in the yellow here is the p block. A p-type sublevel consists of 3 distinct orbitals, each with 2 electrons, for a total of 6. And we can see that the p block is 6 elements across. The same pattern holds for the d block and the f block. So these blocks are given their names because the electrons in the highest energy sublevels are being filled for elements in these blocks. So for example, let's say we pick lithium, element number 3 right here. Lithium is in the S block and in the second period. So that tells me its highest energy electrons are in the 2s sublevel. What about over here? Think carbon. Carbon is in the second period, but over in the p block. So that tells me its highest energy electrons are in the 2p sublevel. So the period and the block that an element is found in tells you what sublevel its valence or highest energy or outermost electrons are found in. And this is incredibly helpful for navigating bonding and atomic structure. Let's now relate the structure of the periodic table to the order in which orbitals fill. Recall the order for electron filling: the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. And we see that right here. I'm following the arrows: 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on. So if an element has only one electron, it will fill the lowest energy orbital, 1s, my first one there. Well, which element has only one electron? That would be hydrogen. The next element is also going to fill in the 1s because there are space for 2 electrons in an s orbital. And we see that over there, helium. After the s sublevel fills, we move to the next highest energy level, and that would be the 2s sublevel. Element number 3, lithium, right there, is found in the s block and is in the second period. So lithium, beryllium, elements 3 and 4, fill the 2s sublevel. And so as you can see, as I move from the element with the lowest atomic number, left to right, and then top to bottom, I'm increasing the number of electrons. As I move from block to block, I have to start a new sublevel. So let's look at the order in which orbitals fill using the periodic table. 1s, 2s, 2p, 3s, 3p, 4s, and then 3d right there. Now I'll stop right there because let's notice some pattern here. When we're looking at the s blocks and the p blocks, the period matches with the energy level for that block. Elements in the second period in the s block, it's the 2s sublevel, and then so on with the 2p. And if you look down here, the 6p sublevel is found in this p block of the 6th period. So the period tells you the main energy level. For the d block, the main energy of the level of d block is 1 lower than the period. So if we're in the 4th period, that sublevel is the 3d sublevel. So the D sublevels lag behind the S sublevels. 4S, 3D. Sixth period, the 5D. Now we haven't done too many examples with the F subblock yet, which I obviously didn't write properly. But you can see the same pattern here, but it's actually the F sublevels are 2 behind the period. So when we're in the 6th period, is filling the F4F sublevel. At the 7th period, we're filling the 5F sublevel. So we are 2 main energy levels behind in terms of matching the period with the F block. So as you can see here, a helpful way to figure out electron configuration is using the periodic table.